Hello everybody, welcome to the second lesson for this series. We're going to do equations of lines. So there's not too much theory for this one, so it's mainly going to be examples, which should hopefully make it so it's on a 44-minute video. So looking at this, we've got horizontal and vertical lines. Now the vertical line through a point, any point, so vertical, straight up and down, like this, is given as x is equal to a, so it's just that point that is, or the ordinate of that point there. So if I've got a point and that is 3, 2, then a vertical line that goes through the point 3, 2. So 3, 2 is over here, then a vertical line that goes through that point must be where x is equal to 3, and so that's the equation of my line. Okay, it's pretty simple. And for a horizontal line, it's the, goodbye thing, it's exactly the same, except we have, we're using the second one, so the y part. So again, if our point is 3, 2, so let's say it's here, then the horizontal line is going through where y is equal to 2. And it doesn't matter which points along my along this line I pick, 2 is always going to be the solution. So if I pick this point here, okay, so this might be at -1, but where x is -1, y is equal to 2. And that's how we get our line. So it's made up of all the points where y is 2. So disregarding what the x is, where the y is. Now the gradient intercept form is the line with gradient m and y-intercept c is, we give it as y is equal to mx plus c. Okay, so this is our gradient. C now is our y-intercept. I know you guys like using b, but the times have changed. Now the gradient intercept form you've been doing since like year 8, I want to say, maybe year 9, more formally in year 9, but year 8 is when you first look at it. The general form of a equation, however, I think we only have a little bit of a look at in year 10, but it's basically when everything is on the other side. So let's say we have our equation, y is equal to 3x plus 2, then our general form for this would be y minus 3x minus 2 is equal to 0. So everything is on the left-hand side and we're left with 0 on the right-hand side. But sometimes when we have these equations, we might have a half x plus 5, okay? And we don't like having these fractions when we have our general form. So once we move everything to the same side, so y minus 1/5, 1/2 x plus 5, well, I don't like having that fraction on the bottom, or that fraction there, so what we're going to do is going to remove it by multiplying everything by 2. So 2 times y is 2y, 2 times a half x is just x. That should be a minus 5, not a plus 5. And then 5 times 2 is -10, and is equal to 0 times 2, well, that's just still 0, okay? So a general form is just with everything on one side and with no fractions. So how is this related, or what are we actually going to see this for? Let's have a look at our first example. So what we're going to do is we're going to write down the gradient and the y-intercept of the line, L, y is equal to 3 minus 5x, okay? So gradient is your value that's in front of your x. So that's this guy here. I also apologize for all the noise that's everywhere because schools are apparently a busy place when there's no one here. And this part here is our y-intercept, okay? So for part A, the gradient, so we call gradient m is equal to -5 because it has a negative with it. And C, our y-intercept is 3. Find the equation of a line through 0, 5 that is parallel to L. Okay, so if a line is parallel, we remember from yesterday that a parallel line, or two lines are parallel if and only if, that's what IFF means, if and only if. So lines are parallel if and only if the gradients are the same. Okay. So parallel if and only if the gradients are the same. So if the gradients are the same, we can work out what the y-intercept is by using a point. Okay, so we know that our equation must be y is equal to, well, we don't know what our y-intercept is. So C minus, we know our gradient must be 5, okay, because it has to be the same for it to be parallel. So this is the equation. Now we need to find out what our y-intercept is. We can do this by substituting a point, 0, 5. Okay, so if we substitute that point where this is x and this is y into this equation, I should get an equation where this line exists, or where I should get an equation for this line. So substituting values in, so where y is equal to 5, I get 5 minus c lot, or is equal to c minus 5 lots of 0. Okay, so 5 is just equal to c, so c is equal to 5. So my equation becomes y is equal to 5 minus 5x, and that's it, okay? So just by substituting, by using the same gradient, but not knowing what c is, and substituting that single point where the y and the x are, we can work out what c is and then come up with an equation for every possible line. Now, part C says to find a line that's perpendicular with that same point there. So a line that's perpendicular, okay, and I'm going to use this phrase again, if and only if, so IFF. It's just a maths term that we use, a shorthand way of running that. So perpendicular if and only if m1 times m2 is equal to -1, or m1 is equal to the negative reciprocal of the other. So to do that, we know that our gradient for so if m2 is equal to -5, then m1 is equal to -1 over -5. So m1 is equal to 1/5. So if we know that's equal to 1/5, then we can work out what the, now we can write our equation. So go y is equal to, okay, we don't know what the c or the y-intercept is yet, but we do know that our gradient is 1/5, and our value there, and we have an x there. Now to find the value for c, we're going to do the same thing again. So the point we're going to be using is 0,5 again. So when we have this point, 0,5, we can substitute it in where that is x and that is y, and we get 5 is equal to c minus 1/5 lots of 0. Okay, and just like before, the 5th times 0 is going to cancel out. We're going to be left with 5 is equal to c, or c is equal to 5. Now with that, we can substitute the c back into my original equation, which we get y is equal to 5 minus 1/5 x, and that is my line that is perpendicular to the original line with an equation that's perpendicular to the original line through the point 0,5. Now, a shorthand way of saying that is actually looking at the points that we're using, 0,5. Those are already y-intercepts, so we actually don't even need to work out the y-intercept this long way. But sometimes you might have to, because it might not be a point that's a y-intercept. And the reason I know this is a y-intercept point is because when x is equal to 0 is where my y-intercept is. So this point is 0,5, that's up there. So that must be the y-int. Okay, so that's example 1. Okay, example 2. Put the equation of the line 6x minus 4y plus 5 is equal to 0 in gradient intercept form. So that is, we just want to work out, or we just want to rearrange this equation effectively for y. So we've got, in fact, I might change my pen so it's a bit thicker, not that thickness. I don't like this really thin pen. Okay, so that's better. A is, we've got 6x minus 4y plus 5. So we want a positive y by itself. So the easiest thing to do in this case would probably to move the 4 over to the other side because it's negative already. So the opposite of minus 4 is plus 4y, and then plus 4y. So that leaves us with 6x plus 5 is equal to 4y. Now I want to get the y by itself. So I can rewrite this as 4y is equal to 6x plus 5. I'm allowed to rearrange it like that. But what we're going to do now is we're going to try and get the y by itself. And to do that, if you guessed correctly, we're going to divide everything by 4. So y is equal to, so 6x divided by 4. So 6 divided by 4 is, as a fraction, 3 on 2x. And then plus 5 on 4 as our last little bit. Or alternatively, you could just write that as y is equal to 6x plus 4. Actually, no, don't do that. Do it the way I did. So I'll just do that one again really quickly. Not 4y, so y is equal to, so 6x, 6 over 4x plus 5 over 4. And we can simplify 6 over 4 to 3 over 2x plus 5 over 4. Okay, So hence, write down the gradient and the y-intercept of the line 6x minus 4y plus 5 is equal to 0. So the general equation that we had up here and the y-intercept or the gradient-intercept form equation that we have down here are exactly the same equation. So when I'm asked to find the gradient and the y-intercept of this, the easiest way to do it is to literally just rearrange it into gradient-intercept form. So if we just gave you part B, you would have to do this step first and then actually find what the gradient and y-intercept is. But since we've already got it, gradient is equal to 3 over 2 because that's the number in front of the x, and C, our y-intercept is 5 on 4. Okay, and that's those two. So last bit pretty easy. So again, gradient is just the number in front of the x, the y-intercept is the number by itself, because remember, to find the y-intercept, you let x be equal to 0, and then that will just cause all the x terms to disappear. Okay, last but not least, find in general form the equation of a line passing through 0, -5 and perpendicular to the line with gradient 4, 5. Okay, so for part A, if the gradient of the first one is 4 over 5, then the gradient of the second one must be the negative reciprocal, so -5 on 4. Now we know it passes through the line 0, -5, so we can work out what the y-intercept is. Well, we don't even have to. We already know what the y-intercept is because it is that last little bit there. Okay, it's the -5, but we'll do it the long way just to make sure that it works. Okay, so my equation of my new line is y is equal to mx plus c. Substitute my m, get y is equal to -5 on 4x plus, and I'll make that 5 look a bit nicer because that kind of looks like a 3. -5 on 4x plus c. Okay, sub in c, we get -5 is equal to -5 on 4 lots of 0 plus c. So c must be equal to -5. So my equation becomes y is equal to, so my gradient, -5 on 4x plus -5 or just -5, okay? And so that's my equation for that line there. That is perpendicular to the line with a gradient 4 on 5. Now part B is a little bit different. It has having an angle of inclination of 60 degrees. Now this is really important that we remember where our tan ratios come from, because this is what we're going to be doing. So basically my graph is going to look something like this. I don't know what it's going to look like, but we know already that it's going to go through -5 because of the point up above in the C. And we also know that this angle in here, this alpha, is equal to 60 degrees. Okay, so this 60 degrees here is how big or what the angle is in between there. So we need to work out what the rise and the run is of this triangle. Now I'm judging that you guys don't quite remember how we get the trig ratios or how we know what 60 degrees is equal to. Now this is really important where our exact ratios come into. So the first way is you just remember what it is. And I honestly forget, so I'm going to do it the actual way, like the longer way. So the way that we get our 60 degree ratio is we start off with an equilateral triangle, okay? So where we have 60 degrees in each of our corners, okay? So with each of those 60 degrees, what I'm going to do is I'm going to, and it has, can't forget the most important part, lengths of 2, okay? So lengths of 2, okay, and it's 60 degrees in each corner. What I'm going to do is I'm going to cut this triangle in half, okay? And so when I do that, what I get with this triangle, it's a right angle triangle, I get 1 down here, I get 2 down here, and if we apply Pythagoras, we get 2 squared minus 1 squared, which is just equal to the square root of 3, or the square root of 2 squared minus 1 squared, which is the square root of 3. Now my angles, well, this angle down here is going to stay intact when I move it across, so that's still 60 degrees. I've got 90 degrees down here, but this angle up the top is actually going to split in half, and it becomes 30 degrees here. And so this is where we get our trig ratios for 60 degrees and 30 degrees. This is where our exact values come from. So using tan is equal to, or tan of 60 degrees is equal to the opposite over the adjacent. Okay, so we get tan of 60 degrees is equal to, so we use our 60 degrees down here. My opposite is root 3. My adjacent is equal to 1. So tan of 60 degrees is equal to square root of 3. So my gradient So remember from the other day, m is just equal to, or tan alpha, or tan whatever you want to call it, is just equal to m. So we've got tan of 60 degrees, so is equal to root 3, so therefore m must be equal to root 3. Okay, so now when I put these into my equation, so we go y is equal to mx plus c. I know what my gradient is. Y is equal to root 3 of x plus c. And we're allowed to have square roots of 3 as our gradients. There's nothing stopping us from doing that. So with this square root of 3 now, I can use my other point, my b. Well, we can sub, I should write sub in c. I think we've got c, which is 0, negative 5. Okay, so if we sub this point in, we're going to get negative 5 is equal to root 3 of x, not root 3 of x, root 3 of 0 plus c. And again, our c is just equal to negative 5. And we knew that already because our point we were using was on the y, was the intercept. So therefore, my equation becomes, for a line with gradient root 3, becomes y is equal to square root of 3x minus 5. That goes through that point. Okay. So those are all the examples for this one. Please let me know if you have any troubles or you need any help with those. And I will see you guys hopefully soon, but maybe not. See you later.